Let's do the review problems for chapter 16, our last chapter. Snoopy-doo. Woo-woo. Okay, define the following terms. So a chemical equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. B, Le Chatelier's principle is when an equilibrium is stressed, it will shift to relieve the stress and reestablish equilibrium. Acid ionization constant is the equilibrium constant for a reaction between an acid and water. And a base ionization constant is the constant for a reaction between a base and the water. Number 2, when you first mix the reactants in an equilibrium reaction, which reaction, forward or reverse, is the faster one? Usually, the faster one is going to be the forward reaction when you first get started. As time goes on, which reaction slows down and which reaction speeds up? As time goes on, the forward reaction will slow down and the reverse reaction will speed up. Number 3, a student measures the concentration of products in an equilibrium reaction and sees that they are changing. Over time, however, the concentration levels off and stops changing. The student decides that the reaction must have stopped. Is the student correct? Why or why not? Because no, the student is not correct because these reactions never fully stop. I told you in class that even though the concentrations stop changing, we have reactants constantly going to products and products constantly breaking back down and going into the reactants again. So they're just doing it at an equal speed and therefore a rate, I should say, an equal rate, and therefore the concentrations are no longer changing, but the reactions continue happening. It's just the concentrations don't change. So the student is not correct. The reaction doesn't really stop. Number 4, the rate of the forward reaction, which is in the blue in this graph, and reverse reaction, which is in the red, for an equilibrium reaction are graphed on the right. At what time did the reaction first reach equilibrium? So you look at where they came together in the first place. I'm going to go ahead and draw this. So to find the first equilibrium, you would go here and go to the bottom and see what the time is. And the time there is right at 250. Don't worry about getting perfect, just 250 seconds, 250 seconds. And at what time was the equilibrium disturbed? You'd go over here and look for this place and look where that is. That's where it was disturbed. And so in this particular case, that would be right around 400 seconds. And then it says at what time did the reaction reach equilibrium after being disturbed. That would be here. And so you'd go down and that would be right around 500 seconds. Now you could have said 510 or 410, something in there. But get it in the right range and we'll know you're looking at the right place. So this is where it came to equilibrium in the first place. This is where you added reactants, so it shifted the equilibrium, and the equilibrium was reestablished here, so this would be where it was stressed. Number 5, the equilibrium constant for a particular reaction is given by, and then we've got that equation. What is the balanced chemical equation for this equilibrium? Well, we're just working backwards here. We know that the reactants are in the denominator, so we would start with those, and that is to the 4th power in this equation, therefore the stoichiometric coefficient is 4, plus we have 6 waters, and these have to be gases, don't they? But he didn't ask you for that, but I'm just saying. And then we're going to go like this. Then we go to the numerator, and we have 4 NH3 plus 5 O2. And I just wrote that in because I know that's got to be a water vapor because otherwise it wouldn't show up here, would it? And so all of these either have to be gases or in the aqueous phase. And they don't need to be written in here, so don't worry about that. But this is taking the denominator, and there's your coefficient is the exponent in this equation. There's the water, there's the exponent. And then you go up to the numerator, that one, there's the exponent as the stoichiometric coefficient, that one, and there's the exponent as the stoichiometric coefficient. So you're literally just working backwards. Number 6, A chemist starts with carbon monoxide at that concentration and hydrogen at that concentration to start the following reaction. At 930 degrees Celsius, oh yeah, that's the reaction. At 930 degrees Celsius, the equilibrium concentrations are found to be as follows. And there's your concentrations at equilibrium. What is the equilibrium constant? Okay, so we're going to ignore the initial concentrations to do this, and we're going to go straight to the concentrations at equilibrium. So we have, the products are on the top. That's a gas. This water is a gas, so we can include that. Carbon monoxide is a gas, and the hydrogen is a gas, and it has a stoichiometric coefficient of 3, therefore it's got an exponent of 3. Okay, now, remember, this is all true at equilibrium concentrations, and that's why he was kind enough to write that in there. So you're going to take the equilibrium concentrations, and so we're going to plug those in. Okay, there I've plugged in their concentrations at equilibrium. And so we have 3 significant figures in each place. So when you do the math, you end up with 4.18. This is molar squared over molar to the 4th. So that's going to give me 1 over molar squared. So the equilibrium constant would be 4.18, 1 over molar squared. So we did the equation. We plugged in the concentrations at equilibrium. We watched our significant figures, got the 3 digits there, and then we worked out the units. I work them out separately. It's just easier. I want to see them and I want to be able to cancel them out. Number 7, the equilibrium constant for the following reaction at 900 degrees Celsius is 27.81 per molar squared. At equilibrium, and we're given all these concentrations, what is the concentration of CS2 at equilibrium? So what we do is we go ahead and make our equation, and these are all gases, so they're all going to get in here. Okay, so I have everybody there. All right, now we're going to plug in what we're given. We're given that this whole thing is 27.8, 1 over molar squared. We're told at equilibrium the concentrations. We don't know what this is. That's what we're looking for. And H2 is 0.115 molar. There we go. So we wrote up our equation. We plugged in where he gave us numbers, and this is what we're trying to find. So what I'm going to do is multiply both sides by CS squared and divide both sides by this. So I'm going to go ahead and bring this over here. And I multiplied both sides by the CS concentration. Okay, there we go. And so now we just do the math. We have 3 significant figures in each of these places. So now we have 3, 3, 3, but we have 2 significant figures here. So go ahead and do your multiplication and division. You're going to be left with 0.025. And then we have molar to the 3rd on top. And down here we have molar to the 4th over molar squared, so that's going to end up giving us molar squared. I just want to show you. Molar to the 4th over molar squared, that's what this is. So that's going to cancel this and leave this with 2. So that's going to be molar cubed over molar squared, which is going to give you molar. There's your answer. So your answer is going to be that the concentration of this is 0.025 molar. And that's how we found it. We just plugged everything else in, then we multiplied by this, divided by this. Watch your exponents and your significant figures. And if you end up getting a strange unit, go back and look and make sure that you've done all your exponents correctly, because that's the kind of mistake I would make. So I'm just telling you. Okay. Number 8, given the information below, write each reaction as a one-way reaction if possible. If not, indicate which side the equilibrium is weighted toward. Now remember, if the equilibrium constant is 1,000,000 or above, or 1 millionth or below, then we're going to write the arrow in just one direction. If it's less than that, then we're going to write the equilibrium going both ways, and we can say which way it's weighted towards. If it's greater than 1, it's weighted toward the products. If it's less than 1, a fractional number, is weighted toward the reactants. Because remember, the equilibrium constant is the concentrations of the products divided by the concentration of the reactants. And so the first one has a K of 4.3. So this, on the first one, on A, we are definitely going to keep our equilibrium arrow going both ways, but it is 4.3, and therefore it's weighted toward the product side. So it's definitely weighted toward the product side because it's greater than 1. On B, the number is a huge number. The equilibrium constant is a huge number, so we are just going to write the arrow going towards the product side. We're not even going to bother to do an equilibrium sign. On C, the number is a fractional number, and so, but it is not a millionth, 1/1,000,000th or less. Therefore, we are still going to write the equilibrium sign, but because it's less than 1, it's weighted toward the reactants. And with D, it's above 1,000,000. This number is huge. Small. I just saw the negative. 4.5 times 10 to the negative 31st. It's an extremely small number. So we would want to write it in this direction. But because we're not allowed to leave it like that, we are going to flip it. We are going to write it as 2NO, which is the product, and then we're going to go with our arrow to the right, and then we're going to go N2 gas plus O2 gas. And that's how we would write that one. So we would actually, because it's weighted so heavily to the reactant side, we would flip the whole thing and just write it towards what was the reactants, but now are the products. We flipped the whole thing, and that's because it was such a small number. Number 9, write the equation for the equilibrium constant of the following reactions. So here we're actually watching for the solids and the liquids to drop out. The only ones that will keep are the gases and the aqueous solutions. And so the first one we would write on A, that is a gas product, so we can keep it. And carbon is a solid, we're not going to keep that, but the other one is a gas, carbon dioxide, so we're going to keep that. And that would be, for A, the equilibrium constant, the equation for the equilibrium constant. For B, sodium carbonate is a solid, so we're not going to include that. Water is a liquid, we're not going to include that. So we get over to CO2, gas. And then we go to the reactant side, and it's a solid, so we're not going to keep that. So that is going to be our equation for our equilibrium constant, because we have to drop the solids and the liquids out. So that's it for B. Number 10. A chemist is studying the following chemical reaction at 25 degrees. And we have the reaction there, and we have the equilibrium constant given to us as a small number. It's definitely less than 1. For each of the following situations, determine if the reaction is at equilibrium. If it isn't, indicate which way it must shift to reach equilibrium. Okay, so we're going to have to do the work here to figure that out. So let's see, we've got all gases, so we're going to include everybody. Okay, and I included my stoichiometric coefficients. Good. All right, so for this first situation, we're going to put in, there we go. We have 3 significant figures each place. When you do the math for that, you're going to end up with 4.34 times 10 to the negative 4th molar. Now we were given that the equilibrium, I'm going to write it here, that the equilibrium is 0. Which is actually 4.34 times 10 to the negative 4th. So A is at equilibrium. It's dead on at equilibrium. Okay, next one, let's do. Still all 3 significant figures. We come up with 6.62 times 10 to the negative 3rd molar. Now remember, this is actually 4.34 times 10 to the negative 4th molar, just so you can see it. So this is a larger number than this one, isn't it? And if you want, I'll write it out this way. so that you can see it. There it is. So now you can see it. This is a larger number. If this is a larger number than the equilibrium, we know that we have to make it smaller, so it's going to shift to the reactant side. So this is not at equilibrium, and it'll have to shift to the reactant side to get to equilibrium, because this number is larger than this number. And then for C, okay, we have 3 significant figures, 3, 3. So when we do this, we get 9.28 times 10 to the -5th molar. Remember, this is 4.34 times 10 to the -4th molar. So this number is smaller than this number. Therefore, this is not at equilibrium, and to make it larger, it's going to shift to the product side. So this is not at equilibrium, and it will shift to the product side to reach equilibrium. Number 11, fill in the blank. Salt melts ice by disturbing the equilibrium that exists between the solid and liquid phases of water. Number 12, the following reaction reaches equilibrium, and then we are going to stress that equilibrium and see what we get. Now, this is the equation that's in your book, but I haven't put in the energy, and it tells us that the enthalpy is -145 kilojoules. A negative is an exothermic reaction, so I'm going to add it over here, plus 145 kilojoules. Okay, so we have our heat added into our reaction. A says if the temperature is increased. So we're going to increase the temperature as our first thing. That's going to push everything in this direction. So these guys will all go up, and these guys will all go down. And we're asked about what happens to this guy, so it decreases. On the next one, we're going to add H2SO3. H2SO3 is aqueous, so that is going to matter. I'm going to add that. This is going to push everything in this direction, so these guys are going to go down, and these guys are going to go up. And the one he asked about was the same one. In this case, it increases. Now, if we remove H+, is that what we're doing? Yes, removing H+, there it is. It's going to pull everything in this direction, so these are going to go up, and these are going to go down. And so once again, he asked about this guy. So this guy increases if you remove this guy, because it's pulling everything in this direction. And the last one, we're asked if copper is added, which is this one. Well, this is a solid, so it's not going to change the concentrations, and therefore the equilibrium is not going to be stressed or shift. So there's no change. So it asked about what would happen with this guy again, and I would say no change at all. Remember, liquids or solids, they don't change them. They're affected by what happens around them, but changes in the liquid or the solid do not affect the other ones, because it doesn't change the concentration, because their concentrations don't change. Let's go to 13, and we're doing another one, and we're going to stress it. Okay, we are given the enthalpy as a positive number. That means it's endothermic, so I'm going to write it over here. First thing, we're going to increase the pressure. Now, remember, when you increase the pressure with gases, it's going to move away from where the most gases are. Here we have 1 mole of gas. Here we have 3 moles of gas. So if we increase the pressure, these are going to go down, and this is going to go up. And so the question was, what happens to H2? And it will decrease. Okay, the next one, the pressure is decreased. Now, if I decrease the pressure, it's going to move back to where there's the most moles of gas, and this one's going to decrease. And so we're looking for what happens to water. It's going to decrease in this case. The last one, it says we're going to decrease the temperature. If we decrease the temperature, then everything's going to move in this direction. So this is going to go up, and these are going to go down. And so it's asking about O2. So O2 is going to go down. It'll decrease. Like I said, I would do the whole thing. Don't just answer one question. Answer all of it. Make sure you're doing it right, and then pick the one that he asked for. Number 14. 3 beakers contain 3 different acids, all of the same concentration. The pH of the solution in A is 1.4, B is 5.1, and C is 3.2. The acid ionization constants of the three, and then they are given there. Match the ionization constant to the beaker that contains the corresponding acid. All right, well, we are strictly looking at acids here, so we're going to go from 0 to 7. I know it continues on to 14, but we're dealing with acids. And we see in the first beaker it's 1.4. So beaker A is 1.4. Beaker C is 3.2, and beaker B, I'm just putting them in order of their pH, is 5.1. So I know 7's got to be out here a little further, doesn't it? Okay, there you go. All right, so now we know that this is the strongest acid, so it's going to have the highest acid ionization. So the number that looks like it's the biggest number there is this one. And then progressively going this way, 4.5, -6 molar. And then this one is the weakest one, so it has the smallest ionization constant. There we go. So we have the largest ionization constant to the strongest acid, and the weakest ionization constant to the weakest acid, which is B, and then C is actually in the middle. I know these aren't in the order, but that's how I have to see them. And so this helps me to be able to figure it out. I hope it doesn't confuse you. 15, two bases at the same concentration have different pHs. One is 14, the other is 10. Which of them is the weaker base? The one that is at 10 is the weaker base. The one at 14 is the stronger base. Remember, they get stronger on the ends. So the strongest acids have the lowest numbers. The strongest bases have the highest numbers on the pH scale. Number 16, what is the equation for the acid ionization constant of HCN? Now remember, when we do these, we're just going to add, we're going to take them as aqueous, and we are going to add liquid water to this. That's how we find the acid ionization constant. And so then this is an acid-base reaction, so this is going to give up the proton. So we're going to end up with this. Whoops, don't forget your little sign there. There we go, got that backwards. Don't forget your sign. Don't forget your sign. You add your acid to liquid water, do the acid-base reaction, don't neglect your signs. And then we were asked for the acid ionization constant, so you're going to go like this, and you're going to grab these two, over, this one is a liquid, so you're not going to include it. There you go. And so that is your acid ionization constant for HCN. Do the reaction and then put it up here. How do I know the water's liquid? I have it memorized. How do I know the other ones are aqueous? I have it memorized. You just need to know that. Number 17, what is the equation for the base ionization constant of CH5N? And this time we're doing a base. Because we're doing a base, this guy is going to receive the proton, the hydrogen, and therefore it'll get the positive. This is going to be left as OH, it will get the negative. And then we're going to do the equation by including everything in the aqueous phase. But we're going to leave the water out. So that, for number 17, would be your base ionization constant. That's the equation. That's how we make it into the base ionization constant. Number 18, the base ionization for NH3 is 1.8 times 10 to the negative fifth. The base ionization for C2H7N is 5.1 times 10 to the negative fourth. At the same concentration, which produces the higher pH? Well, we're looking at bases here, so we're between 7 and 14. The higher pH is the stronger base. So you look for which one has the larger number there for its base ionization constant. And in this case, the second one is 5.1 times 10 to the negative fourth molar. And therefore, that one, C2H7N, is going to be the one with the higher pH because it's got the larger number for its base ionization constant. Okay, guys, you've done a great job. I want you to go ahead and study this. If you need the extra practice problems, they're loaded on YouTube for you. Go ahead and take your test. Grading the test is there on YouTube for you to get through that. Thank you for doing chemistry with me and for persevering to this point. I'm very proud of all of you. Just keep your eyes fixed on Jesus, the author and perfecter of your faith, throughout your life. Remember that you can trust him no matter what is going on around you. You can absolutely trust him. He's got your back. He doesn't promise you're not going to suffer here. As a matter of fact, he promises the opposite, that in this life we will have trials and tribulations and suffering, especially if you choose to follow him. But we are promised that he will be with us through it all, that we can trust him in it, and that we will spend eternity with him. Praise the Lord. So keep your eyes on him. Stay in God's word. Thank you for persevering through chemistry with me, and I hope and pray that I will see you all again. God bless you, and may Jesus overwhelmingly bless you in your life.